So, have you ever wondered how an app can look at just a chaotic mess of data and somehow pull out a single confident prediction? Well, today we're going to go on that exact journey from pure guesswork to actual powerful prediction. Let's dive in. I mean, think about the last time you ordered some food. You get that notification, right? Arriving in 22 minutes. Where does that number even come from? Is it just a lucky guess, or is there some serious heavy duty math happening behind the scenes? That's exactly the kind of question we're going to unpack. Okay, to make this super real, let's put ourselves in the shoes of a grocery store manager. We've got a pile of data on all our past deliveries, how far they went and exactly how long each one took. Our job is to use this history to make promises to new customers that we can actually keep. All right, so where do we even start? Before we get all fancy with complicated models, we need a baseline. We need a starting point. What's the absolute simplest, most basic prediction we could possibly make? Well, it's the good old mean, the average. You just add up all your past delivery times, divide by how many trips you made, and you get one number. Let's say it's 22 minutes. That's our starting line. Any other model we build, no matter how clever, has to be better than just shouting 22 minutes for every single order. But wait, before we even try to predict anything, we need a quick sanity check. I mean, do the things we're measuring, like the distance of a delivery and the time it takes, do they even have a real relationship? That's where the correlation coefficient comes in. Think of it as a score that tells you if two things are like dancing partners or if they're just total strangers ignoring each other on the dance floor. So this score, we call it R, and it's always somewhere between -1 and +1. If you get a score close to +1, say plus zero point 0.9, that's great. It means as distance goes up, time goes up right alongside it. A score near -1 means the opposite. And a score of 0, that means there is absolutely no connection, and trying to use distance to predict time would be a total waste of our time. Okay, now we need a way to measure just how bad our simple 22 minutes guess is. And for that, we have SST. Seriously, just think of it as the total mess. It's the huge giant error score you get from just using the average over and over again. It represents all the chaos we're trying to fix. This is the score to beat. You see, the problem with the average is it's a blunt instrument. It's way too slow for customers who live nearby and way too fast for the ones far away. So it's time for an upgrade. Let's bring in a new piece of information to help us draw a much smarter line. So here's what we do. We plot all of our past deliveries on a graph. We put distance on the bottom axis and the time it took on the side axis. The whole goal here is to draw one single straight line that best weaves its way through all those little data points. This simple but incredibly powerful technique is the heart of what we call linear regression. Now, even with our awesome new line, we're not going to be perfect, right? The little gaps between each actual delivery and our prediction line, that's the error that's still left. When we add up all those little bits of error, we get SSE, or the sum of squared errors. I like to call this the leftover mess. And our whole goal is to make this leftover mess as tiny as possible. So how do we grade our new model? How do we know if we did a good job? We use a fantastic score called R-squared. And the logic behind it is actually really beautiful. First, you just figure out the ratio of your leftover mess to the total mess you started with. Then you subtract that number from 1. And what's left is the percentage of the original chaos that your new, smarter model managed to clean up. And get this, here's the really cool part. This R-squared score is literally just our correlation coefficient R from our sanity check, squared. It all connects. So for example, if you get an R-squared of 0.80, what does that actually mean? It means your model, just by using distance, has explained away 80% of the total mess in delivery times. That is huge. You can think of it as your improvement score. And honestly, it's probably the single most important number for telling you, at a glance, how good your model is. All right, we have a model, we have a great score, we're feeling pretty good about ourselves. But hold on, this whole thing was built on just a sample of our deliveries. Can we really trust it? Can we bet the business on it? It's time for some serious quality control. First up is something called the confidence interval. Just think of this as your safety net. Because we only used a sample of the data, not every delivery ever made, we can't be 100% certain about anything. So instead of giving a single number, we give a range. We'd say something like, we are 95% confident the true average is somewhere between 18 and 26 minutes. It just keeps us honest about what we don't know for sure. Next, we've got to check if our model gets sloppy over time. In a good model, the errors are just a random, fluffy cloud. It's just as good at predicting short trips as it is long trips. But if your errors start to form a megaphone shape, getting wider and more unpredictable the further out you go, whoa, that is a huge red flag. It's telling you your model just can't be trusted for those long-distance deliveries. And here's another problem to watch out for. It's got a super fancy name, multicollinearity. Don't worry, it's just a complicated way of saying you're using redundant information. Just imagine trying to predict delivery time using both distance in kilometers and distance in miles. They're telling you the exact same thing. It just confuses the model. The rule is simple. You have to pick one and delete the other.
Okay, deep breath. We've pretty much gotten the hang of predicting a number, like time. But what if the question we want to answer is a choice? A simple yes or no. Like, for example, will a customer leave a tip? This is a whole new ballgame.
See, the problem is you can't just draw a straight line through a bunch of yes and no answers. It doesn't work. So first, we have to completely change how we think about probability. We switch over to using odds, and it's really just a simple ratio of winners to losers. So if 80 people tipped and 20 didn't, the odds of someone tipping are 80 to 20, or 4 to 1.
But that still doesn't quite solve our central challenge. Odds are always a positive number, right? You can't have negative odds. But our trusty linear model, that line can go anywhere, even into negative territory. So how on earth do you draw a straight line through simple yes or no answers? The answer is a really clever, kind of beautiful math trick called the logit, or log odds. By taking the logarithm of the odds, we basically stretch the scale. It transforms our positive-only odds into a number that can go all the way from negative infinity to positive infinity. And just like that, boom, we can finally use our linear model to tackle a yes or no question.
Okay, so how do we grade this new kind of model? We use something called a confusion matrix. It sounds complicated, but I promise it's really just a simple 4-box scorecard. It compares what we predicted to what actually happened. Did we predict yes, and they really did tip? That's a true positive. Did we predict yes, but they didn't tip? Oof, that's a false positive. It shows us exactly where we were right and where we were wrong. And from this little matrix, we get 3 really important scores. Accuracy is the easy one. What percentage of the time were we right, period? But then it gets more interesting. Recall asks, of all the people who actually tipped, how many of them did our model successfully find? And precision asks, when our model predicted someone would tip, how often was it correct? See, there's a trade-off there, and which one you care about more really depends on the problem you're trying to solve. And that's it. We've gone all the way from a simple, dumb average to predicting numbers and even human choices. We figured out how to build these models, how to test them, and how to score them. These are the fundamental tools you need to find the real patterns hiding in all that noise. So I'll just leave you with this. What patterns are out there waiting to be discovered in the data all around you?